Okay, welcome back to physics. This is the second of three videos. This is going to be a video about finding the electrical field from a semicircle of charge. So let me describe what that's going to look like. So a semicircle, so I'm going to have half a circle, and I'm interested, so there's a charge distributed around the circle. I'm interested at the electric charge that's at this point P. Yeah, two things I'm going to do. So I'm going to take advantage of linear charge density to help me simplify things. And also I'm going to take advantage of symmetry. So what do I mean by that? Well, let me think about this. So I'm going to have a chunk of charge over on this side. And that chunk of charge is going to generate an electrical field that's going to go in this direction. For each chunk of charge on the right side, I have a chunk of charge that's equivalent on the left side. And that's going to be generating an electrical field going in this direction. So hopefully you're recognizing that these are vector quantities, and these vectors are going to have components, and for each of these the horizontal components is going to cancel. So I can use the word symmetry and say, well, listen, the horizontal components are always going to cancel because it's a half circle. So all I'm going to worry about is the vertical components. So this is the first part of it, so you can recognize from the shape that I only need to worry about the vertical components for this. So my electrical field is all going to come from the y components. Second thing that I want to do is I'll have some charge, and it's distributed across this distance here. So say this is a radius r. So the charge is going to be distributed across this semicircle. So I can use linear charge density. So my linear charge density is my total charge divided by my total distance here. This is half a circle, so this is going to be pi r. So half my circle. So my linear charge density, the nice thing about density, of course, is that it's the same for small pieces as big pieces, right? So I'm also going to have some small piece here, so this is going to be dq, some small charge, and that's going to be over some small length here. I'll call that ds because it's really some arc length. And because I'm going to have to evaluate this going around this half circle, that my ds is going to be a challenge. So I'm thinking I'm going to convert that into d theta, right? So you may recall my definition of arc length. So my arc length is going to be r times my radians that I go through. So some small amount of arc length is going to be equal to r times some small amount of radians that I go through. So I'm going to write this differently. So I have my total amount of charge divided by my total amount of arc length is going to be equal to that small amount of charge divided by r times that small angle that it's passing through. And with this, I can get to an expression for the small amount of charge. So this is usually the problem that we have. So I'm going to have two things changing, right? I'm going to try to evaluate as I go around, and I'm going to try to then also shrink down that piece to smaller and smaller pieces. So as I shrink down the charge, I've got too many things changing at once. So yeah, I need to change it. So I can use this this equation. So this is going to be q times r times d theta over pi times r. Oh, look, r cancels. And that's handy. So I'm going to get q and d theta over pi. So now I have an expression for that small amount of charge, which is going to be in terms of the radians that I'm passing through. So let me think about this. So now I want to add up all of my y components. Well, let me think about this. So here, let me draw this up a little bit. So I have my here's my point I'm interested in. Right, here's some angle that I have here. So I'm going to define my angle at this point. So I've come up to here, right? So that's going to be generating that small amount of charge here. It's going to be generating some electrical field over here. The angle is going to be the same in here. So I'm worried about is this y component, which is opposite. So this is going to be the sine of my angle is going to get me to that component. Right? So I'm going to be careful how I do this, because what I want to do is I want to evaluate, and I'm deciding, well, I'll start here and evaluate all the way around. You could set your 0 point different, you could arrange it differently, but in this case I'm going to start here, and when I do that I want to be using the sine function. So my electrical field that I'm interested in, the y component, is going to be my total electrical field times the sine of the angle that I'm at. My electrical field now is going to be, well, for the small bit, is kq over r squared overall. But remember, for my small bit, my electrical field is going to be k, that small amount of charge, over radius squared. And then what I want to do is I want to add this all up. So I'm going to now, I'm just going to plug stuff in, right? So I'm going to plug in dq. I'm going to put it into an integral to add it all up. And I'm going to multiply it by the sine of theta, so I just get the y component. Right? So my total amount, right, I'm going to add up, going from 0 to around my half circle, so 0 to pi. I'm going to have k, and then dq, which is this q d theta over pi. Multiply this one over r squared, and I'm going to multiply by sine of theta to get just the y components. Now it looks kind of messy, but there are a lot of constants there, so I can pull this out, and the math isn't quite so bad. Right, so hopefully the concept makes sense. So I'm going to evaluate it over a half circle. I'm going to look at that small amount of charge and just the y component coming from that small amount of charge that's generating the electrical field. So let me do some math. So we'll pull out the constants. So I'm going to have k and q and pi and r squared are all going to come out, and I'm left with 0 to pi for sine theta d theta. Okay, so that makes sense, right? So sine theta, I'm going to look this up on the formula sheet, or you might recall, sine theta is going to be negative cosine. So when I integrate this, I'll have the same constants, kq over pi r squared. And now I'm going to have negative cosine of theta, and I want to evaluate this from 0 to pi. Let's see what we get. So this is going to be kq over pi times r squared. Right? My final, so when I plug pi into cosine theta, I'm going to get negative 1. Right? So as you may recall, the cosine graph is going to go like this and back up. Right? So this is 2 pi. This is going to be pi. This is 0, right? So 1 minus 1. So I'm going to have minus 1 at pi and positive 1 at 0. Right? So I'm going to have cosine of pi is minus 1, negative minus 1. And then I'm going to subtract from that negative 1. Whew. A lot of negatives in there, but anyway, I end up with 2 positives. So in the end, I get 2 kq over pi r squared, which is the formula for an electrical field that comes from a semicircle. And key things, so I used symmetry to focus just on the y components, and I used linear charge density and arc length to get to an expression for dq that involved the changing angle. Anyway, hope that's helpful, and talk to you soon. Bye.